Hello, everyone. My name is Venkat Kapil. I'm a so-called Oppenheimer Research Fellow at the University of Cambridge, and I'm also affiliated with Churchill College. I mainly use machine learning potentials in combination with statistical mechanics to study the phase behavior of systems. And I'm very happy to give not a short, but actually a demonstration of machine learning potentials for materials and chemicals. And the idea here is to cover the basics because that's what I was told. Many of you do not know what these are. So I will really start from scratch here. So this is what it's going to look like. First, we're going to do a short dive into force fields and and first principle methods, and then towards data-driven modeling, which is how do you make a model based on experimental or ab initio data. And up until that point, I'll cover the basics of machine learning, where we will just get used to some of the terminology. And after that, we'll get to machine learning potentials, which will cover some specific things about machine learning for systems, which would also include a bit of physics in there. And eventually, the last bit would be some applications. Of course, the timings here are all tentative. It really depends on what you guys want to focus on and so on. So yeah, I mean, all of this is tentative. At this point, I would like to ask you all to, if you would like, switch on your cameras and I would like to ask a few of you, what are your expectations from this course? Just so that it's not just a one way, it's not a monologue here. So does anybody want to start and tell me what would they like to learn at the end of these 1.5 to 2 hours? Yes, I see one face.
Hi, I use machine learning potentials in my PhD research.
Right.
And I was wondering if we could kind of go over possibly the range of architectures that are available to learn the potential energy surface. Some of the newer stuff, I guess, instead of Baylor, Paranello type networks is currently what I use, but looking more towards the fourth generation and possibly some of the message passing networks potentially as well.
Right. All right, that's good to know. So Kate is probably one of the more advanced members. Amina, is that right?
Yeah. So I work with OPVs, and then I have a big chunk of data. I want to learn to how to interpret this data, because most of the time we target for high efficiencies, but with the different type of material combination and then don't accept a combination, we don't get what we expected. So I am looking into the technological options to get the help, kind of if the machine learning can give us, oh, this is what's happening, this is the how to say, the spectrum or the pattern, then we can easily modify the experiment. Thanks.
All right, yeah, thank you very much. That was an interesting perspective in terms of what people are looking at. Anybody else? I can be the guy who starts taking names. So, all right, Andrea, I know you. Do you want to share with us why you're here?
Hi, Venkat.
Yeah,
I just saw the course. I might be next year. I have to do a similar course, so I was having a look at the structure. I mean, just to take inspiration.
All right. Okay, so I'm happy that this course is also useful in a meta way for others. Anybody else? Okay, show of hands. How many of you have used machine learning potentials or done a bit of machine learning? Let's say, okay, machine learning potentials. Just give me a thumbs up. All right. Is there only one person who's ever used machine learning potentials? Because that's fine, there's no problem. But just to get a picture. How many of you, in that case, how many of you know, let's say, the basics of machine learning? Let's say how many can perform a linear regression? All right, few more people. Many more. Okay. So don't worry, even if you don't know that, we'll cover that. Okay. And how many of you have done something like neural networks or kernel-based models for non-material science or non-chemistry projects? Few of you. Okay, so I think that's that gives me some picture. All right, so let's start with the let's start now. So what I'm going to really start with is materials modeling and some of the basics, And before we get to that, for those of you who are just interested, if you want to learn about kernel-based or Bayesian methods for machine learning, I would highly recommend this book. It's considered a classic. And this is also useful for unsupervised learning or just pattern recognition that some of you may be interested in. And for those of you who are interested in the newer side of statistical learning, then there's this classic book, which also has a free HTML version, so you can access it. And of course, you know better than me how to get free stuff, so I won't get into that. All right. So now let's get back to simulations and start with the dichotomy, which will try to where we will motivate why do we need machine learning potentials. And you may all have seen this plot where you basically have the size of your system that you can treat on one axis and the accuracy on the other. And basically all this plot is trying to show you is that there is an inverse relationship between the efficiency and accuracy of most of the models that we have, where the cheapest models, which can treat very large system size, are these coarse-grained models, which can even represent interaction between proteins, for instance. But then they don't really possess the accuracy of this so-called 1 kilocal per mole, which can be experimentally measured. Then you have a number of classical force fields, which are based on mostly phenomenological terms, which represent interaction between pairs or triplets or quadruplets of atoms. Then there is another class of models called reactive force fields, which have functional forms which even allow you to break bonds. And this is where we start getting closer to the kind of accuracy that you need to simulate chemistry. Beyond that, there are these QM-MM models, which partly treat some important degrees of freedom with quantum mechanics and the rest of the degrees with these so-called classical force fields. And finally, we have these ab initio models, which means models which are based on nothing but just quantum mechanics of electrons and nuclei in your system. And in principle, they possess the accuracy because, well, better nature follow quantum mechanics. Otherwise, we're all just wasting our times here. And if we can solve these equations, then we should be able to predict what's going on, at least for the systems that can be simulated. But of course, I mean, if you want to perform an ab initio simulation, you can only deal with, let's say, thousands of atoms or 10,000 of atoms, depending on the level of theory, with, let's say, maybe a few tens of atoms for the highest levels available, right? Now, why is that a problem? Because generally you don't need to perform just one energy calculation. Now, when you compare your observable with the experiment, anything that you want to model, generally on top of this axis where you get your very high or first principle methods, you also have to generally combine it with some sort of sampling, And the most accurate methods are ones which include the full anharmonicity of your system. And by those, I mean either molecular dynamics or path integral molecular dynamics, if you have heard about that, which also includes the quantum effects arising from the nuclear degrees of freedom. And in principle, if you combine these two, which means a very high level of interatomic interactions and a fully anharmonic description of motion, and that is the point where you will have the highest possible level of accuracy. And currently, because of the large cost of first principle methods, you can generally only combine it with purely static descriptions, harmonic, or when you do MD, you cannot treat very large system sizes. And of course, this is where machine learning potentials will become really handy because they allow you to treat much larger system sizes at the same level of accuracy or comparable level of accuracy as ab initio methods. So it's basically one way of taking your ab initio methods and being able to apply it to much larger system sizes without losing accuracy. All right. Now, before we get to machine learning models, let's discuss the physical models that are generally used and some of their limits. All right. Now, what exactly is a physical model? Well, this is an example of a so-called biological force field, where physical model comprises of terms where each term depends on some sort of a phenomenology. For example, the first term here is the Lennard-Jones interaction, and that is basically an interaction between, which is the r to the power -6, between fluctuating instantaneous charges, right? The second term is the Coulomb interaction, which is basically the interaction of interaction of two charges. Then you have a bond term, an angle harmonic term, and a dihedral term. What is the physical basis of these? Well, when you do X-ray crystallography of proteins, or when you do X-ray crystallography of molecules, you can measure bond lengths. And if a system displays an equilibrium bond length, then that means that it has some sort of a harmonic description around that bond length. Same with the angles, and same with dihedrals, which become very important for molecular systems. Right. Okay, so this is great because we really get to interpret each of these terms here, and one can also modify some of these parameters and really see what is the overall effect on modeling. Right. So that's good. But the moment you start treating systems like atomic systems or ionic systems, these physical terms can start becoming a bit more obscure. For example, some of you may know this is a functional form called the embedded atom model. And the idea here is that you write the total energy as sum of individual energies of atoms, and each atom is embedded in a field. So you have a pairwise description, and on top of that, you have this non-linear energy of an atom in an environment. So immediately you see that, well, it's not that easy to come up with a physical model for an atomic system or ionic system. And you already start getting some abstract functional forms in your physical models. All right. Now there's some things to ponder more in terms of what is the accuracy of these methods. Now, most of these are fitted to empirical thermodynamic data or to ab initio data, right? So the accuracy here really depends on the quality of the data and how you have performed the fitting. For example, if you have data from different temperatures, different pressures, you need to be very careful in how you perform your fitting, right? Now, the second thing is that the accuracy of these models really hinges on the functional forms that you use. And to give a really extreme example, if you have a harmonic potential between two atoms, you will never be able to break a bond, so you won't have any chemistry, right? So here, if you want to simulate a chemical reaction, you will need to use much more complicated models. And thirdly, transferability is usually a problem because you generally fit based on empirical data. Therefore, you should expect trustworthy results while you're simulating that system. But there's no guarantee that these parameters can be used on something else because you don't really have the thermodynamic data for that other system. So that can become a problem here. Now let's see what happens when you start making these models much more accurate. For example, this is an example of the TIP NP family of water models, and these are extremely accurate. The TIP 4P model gives you a very good melting temperature of water, the freezing point of ice, different relative stabilities, and so on. However, you can start seeing that already one starts deviating a bit from the reality of things. For example, this particular model has an additional quasi-particle which is situated at the center of mass of your water molecule. So again, I'm not being critical of this model. I'm just telling you that to get high accuracy, you have to let go of very basic phenomenological models sometimes. And then, of course, to treat chemistry of bond breaking, as I was mentioning in the previous slides, there's this family of Reax force fields, and they have been used to simulate a number of systems, and this tree really gives you a good idea. But if you really look at all of these terms, then you see that there are many of them, and each of them comprises of functional forms which are hard to interpret. For example, most of these are based on a bond order parameter. Now that's something physical, right? It basically measures how many bonds does an atom form. So most of these models are based on some sort of obscure functions of these bond orders. And that really ensures you that as your bond breaks, there is some physical description of your system. But if you really interpret all of these, it's very hard to really say what each of these terms means. The third thing that I want to discuss, and this is, so I'm going to show you some plots, and I really don't want you to get totally confused. I'll just tell you what I really mean to show here, is that if you have a particular functional form and some given data, there is no guarantee that you will be able to treat all properties of your system with a high degree of accuracy. Certain functional forms will give you better properties, which are, let's say, a bit more local, or other functional form might give you properties which are more long range. So it's very hard using empirical force fields to get a model which works on a variety of properties. So here, for example, this is a comparison of different models for silicon. And then in red, you've got the gap potential. Now, gap is a machine learning potential. And now gap is a machine learning potential. And what they have tried to show in this plot is that you not only get low errors for certain properties like surface energies, but consistently on all properties, you get much lower energies. While if you compare these plots for other force field, you'll see that you can get very low energies for some of them, but then that's compensated by much higher energy. So there's a bit of a whack-a-mole going on where you can actually nail one of these properties, but the other one goes bad. And again, another paper from Gabarchani's group and an even more complicated plot. So I'll tell you exactly what to look at. Don't freak out, please. Is that here what they have shown is the density, the error on the density versus the error on the timer energy. And I guess what they're really trying to tell you here is that if you look at all of these models, and these are all empirical models, empirical or data-driven models, which give you the right density, and then the same models actually don't give you a very good description of the dimer energy, while other models which give you a good description of dimer energies don't really give you a very good description of your density. While if you use a gap potential, well, there's one color which you see is spot on. That actually gives you a good description of both of them. So here, you're not in a situation where there's a bit of whack-a-mole going on. You get a systematically better model. All right. So yes, it's difficult to get a fix-all solution when you have a functional form with limited ability. Again, by no means this was a way to say that one of these is better than others. The model that you should choose depends on the kind of application that you're doing, and every model has to be validated. Okay. Now, this is going to bring us to data-driven models, where these models are trained on data produced by first principle methods. Now, what you really, if you run a short simulation for a molecule of water, you will get its trajectory, and then you will get a number of things like its potential energy and its kinetic energy. Now, what can you do with this data? Of course, for water, you can get a very good potential based on bonds and angles. So a harmonic bond and a harmonic angle will already give you a really good model. And then you can also add a few other things like a Morse potential, and that gets you spectroscopic accuracy. But if you do something more complicated than water, that becomes difficult. So the other thing that you can do is that you can go for a more agnostic approach, where you say, well, I mean, my first principle method is already a bit of a black box. At the end, for every configuration, I get an energy and a force, and I don't really know what's happening. I mean, you might know the equations of quantum mechanics, but you don't really know what exactly is the functional form being used, right? So why not just treat this as data and try to use a purely inductive approach, where you say, well, I've got a bunch of data points. How about I fit a curve? And for the next point that I have, let me try to see whether I can make a good prediction or not. And this is a very crude way of explaining an inductive approach for machine learning. Generally, you take your data set, prepare it with much more care. Yeah, but that kind of is the motivation to not really rely on fixed functional form, but to go for something more agnostic. All right. Now, this is going to be one slide on just some of the terminology that typically that you will read or hear about if you attend a talk or if you read a paper on machine learning potentials. So this is just to get everybody at the same level right now. So generally, the end goal in regression or curve fitting is that you have an input which can be a vector, and you have some output which can also be a vector. In this case, this is bold, so I've represented this as a vector. Here, I've treated a simpler case where this is a scalar. The reason, because this has a one-to-one correspondence where what you really want to do is that given your positions, you generally would like to predict the potential energy of the system. So this is like the correspondence between curve fitting and your machine learning potentials. Now, then you have something called a model. A model is basically the function of your input. It has the same dimensionality as your inputs. I'm not talking about the number of input items. I'm talking about what is the dimensionality of this vector. That is the dimensionality of the model. And generally, the way you want to choose your model is that it should be flexible enough to learn any functional form. So if you, in the limit of infinite data, it should have the capability to fit to anything. And there is a class of functions called universal approximators. And these are generally the models that we will consider, as you will see. All right. Now, once you have the model, what you have to do is you have to optimize the parameters of this model. And generally, we'll be dealing with cases where we will have a lot of parameters, more parameters than the number of data points that we have. And the idea is to optimize a so-called loss function. What exactly is a loss? Well, sorry, there's a bit of a mistake here. This F should be an H. So the idea in the loss is that you take your output, and then you take the output of your model, and you try to compute the mean square error on that. And then you take the derivative of this with respect to all the parameters, and you ensure that your model minimizes this loss. Yeah. So, and at the end, the parameters which will give you, which will either completely minimize this, or which will give you a very low error, would be the parameters that you would choose. All right. Now, you would see that there is one more term here called, this is called a regularization term. And I don't know if people here are familiar with overfitting or not, but we'll get to that in a bit. But this basically just prevents your function from fluctuating too much. Here, you're penalizing large values of theta. So if you think in terms of a polynomial, if you add such a term, then if your polynomial takes very big coefficients, they will have a much higher loss. And therefore, it would be better for your model to have smaller coefficients. That means that your model would not fluctuate as much. So it will give you smoother functions in the end. All right. At this point, I would like to stop for a little bit and ask if anybody has any question. And please feel free to interrupt me. If you felt I went a bit fast with all of this, I'm happy to slow down for you. Or if you know all of this, I'm happy to speed it up. Anyone?
Sorry, could you go over the bit from model and loss again?
Right. Okay. I'm happy to. All right. So the idea here is that you have your input data, which is a vector, right? And you have your output, in this case, which is a scalar. Now, your model is basically just a function comprising of many parameters. And that's why this theta is basically just a flattened vector of all the parameters, right? Now, the way you fit your model is that you compute something called a loss function, okay? And the loss function basically measures what exactly is the real output and what is the output of your function. It squares it, and then it sums it over all the data that you have. So what this measures, if you forget about this other term, then what this really, if you just look at this term, what it really measures is the total error exhibited by your model, right? All you have to do is try to make sure this error is low. So generally, you will start with some random values of your theta, which are random values of your parameters, and you'll get a very big error. Then you will compute the gradient of this term with respect to your model parameters, and you will change your parameters to reduce this error. And you'll keep doing this for many, many iterations until you reach a minimum in this loss. Does that answer your question?
Yeah, that helps a lot. Thank you.
All right. Anybody else has a question?
The X values here on your input, are they meant,
Right.
they're meant to be a vector containing the positions of all the atoms, right? In the system?
Yes.
Okay, so that kind of a list of the Qs on the right, that would be one X value.
Right. So this basically means the X coordinate of the first atom, Y coordinate of the first atom, Z coordinate of the first atom.
Input.
Yes.
That whole list would be one input. Yeah.
Exactly. Yeah. Yeah.
Okay.
So sorry, I guess that's a good point. Probably this is a little misleading, but this is basically just one input, right? Yeah.
So your H at the end here is literally just trying
Right.
to approximate U.
In this case, yes, H is a proxy for U in this case. Yeah. And the idea is to
Okay.
choose H such that it can learn anything, and I will discuss two functions formed in the next slide, which have the capacity to learn anything, and then just optimize these parameters until you get a low discrepancy between H and U, if that helps.
Thank you.
Any other question, please shoot. All right, it looks like I can go on to the next slide. Yes, so one of these is an artificial neural network, and in this case, I'm going to discuss the simplest form of that neural network, where what you really see is a graph where there are different layers, and the idea here is that the first layer of a neural network is just your input data, different components of your input data in this case. So for example, if your X is this vector, in that case, what really the blue circle here, what it really represents is one of the components of this Q, right? Now, what the next layer really computes is just a matrix multiplication on these vectors, and then you apply this non-linear function on top of them, right? So this is the next layer that you get, right? So you can already see that if you did not have this obscure function f, all you're doing is that you're basically just multiplying your input vector with a matrix, right? So it's still a linear model in this case, yeah. And then that gives you these points, right? And now the next layer, which in this case would be and the next layer would be again another matrix multiplication of these nodes, and then you will apply yet another function on top of that. So it's a convolution on top of the previous layers. And just to give an idea of what this nonlinear function looks like, well, actually it can be anything as long as it's as long as it obeys some properties, which I won't get into. But one of the more common ones is a sigmoid function in this case, right? So basically the idea is that you take your vector, multiply it with a matrix, and then you apply a sigmoid function on top of that, and that gives you the next set of points. And then you take these, multiply it with another matrix, feed that into another sigmoid function, and so on. And you can keep doing that for as many layers as you like. And ultimately, everything will get contracted to just one output in this case. Now, this already, probably for those of you who are not used to it, this sounds a little complicated, but the idea here is to come up with a function with a capacity. So it will be hard to interpret in this case. But there is still some way of interpreting this. What this sigmoid function really does is that it gives you a 0 or a 1. You can think of it as a smoothened version of a step function. Now, basically, the way to think about it is that you can say that if I have a particular component, I can ask myself, does this contribute in any way to my output or not? Let's say your system is a water molecule, and Q1 is the position of your hydrogen atom. what you really want to ask is, if I move this particular hydrogen atom, is this going to change my energy or not? And if it will contribute, then you'll be closer to a 1. If it is not supposed to contribute, you'll be closer to a 0. So what you're really doing is that when you multiply your vector with this matrix, you are coming up with a linear combination, which can be viewed as a collective mode. And after that, what you do is that you try to ask, does this contribute to my energy or not? And if this linear combination is, let's say, just the center of mass of your system, it should not contribute to your energy. So in that case, this should give you a 0, right? So this is one way of thinking about it. This is definitely not the only way of thinking about it, nor am I saying that all models can be interpreted in this way, but that kind of justifies this particular functional form. Now, the other way of learning something is instead of using a very complicated model, you can process your input data and you can form some complicated, you can form a set of more complicated data, and you can use a simple model on top of it, right? So what am I talking about here? The idea is, in this case, these are called kernel models, or this is called a kernel trick, where if you have a set of data points depicted in gray, which are just, let's say, 2-dimensional in this case. So what you can do here is that you can come up with an arbitrary or an abstract descriptor of this data by selecting some random points in your space. And these are called your landmark points, okay? And what you can try to ask is that for a given data point, how different is it from these landmark points, okay? And in mathematics, this can be thought of as a distance in some abstract space, right? So the idea is that no matter what the dimensionality of your input is, you can ask how far is this point from the first landmark. Then the second bit would be how far is this point from the second landmark, how far is it from the third landmark, and so on. And by choosing a very large number of landmarks, you can make this X as high dimensional as you would like. Right. Now, in terms of a more physical picture of molecules, what you can really say is you can select a bunch of configurations of your water molecules for which you know that water behaves in a particular way. For example, there is an asymmetric stretch in water. So if one of your hydrogen OH bonds is smaller, the other one is supposed to be larger, and so on. So you can come up with a bunch of these configurations. And when you get a new configuration, you can just ask, how different is it from the ones that I already have? And if you have 100 of them, you can generate a 100-dimensional vector where each element of this will tell you how close it is to that. All right. Now, this, for every distance metric, you can show that there is something called a kernel, which basically measures this distance, if you will, in this case, right? So the idea is that the kernel encodes the complexity to define the distance, right? So this is a trick which allows you to create a very high dimensional input. And in this high dimension, because if your kernel has sufficient complexity, you can show that all you need to do is perform a linear regression over these abstract sets of processed inputs, right? So in this case, it's slightly different from the previous case where we had a really complicated model. In this case, our overall model is extremely simple. It's a linear model, but the complexity lies in how you process your data. All right. So broadly speaking, to fit something universally, either you need a really complicated model, or you need to transform your data into something which is extremely complex. And then on top of that, you can use a very simple model. And these are two opposite extremes, or two different ways of going about with machine learning. All right. Does anybody have any question here? I'm happy to answer. Feel free to interrupt me in any case if you have one.
Is the kernel model more prone to overfitting compared to the neural network in that case?
How about we discuss this in the next few slides? But the answer to your question is no, if you're just interested in a yes or no answer. Anybody else has any confusion here?
Venkat, in the last equation,
Yeah.
don't you have to sum also over the landmark points? Not only Li, L1.
Yeah. Yes. Sorry, there's a problem in the notation here, but yeah, you're right here. Anybody has any question here? All right, let's move on then. And this is kind of related to the previous question. Now, let's say I show you 3 plots where all the 3 plots have the same data. You just have different curves. If I ask you a question, which of these is the best model? How would you answer this question, or how would you go about answering this question? Does anybody want to answer this? Savia, since you have had the pleasure of asking a few questions, you become the scapegoat.
Okay.
Uh,
I'd say that the middle model is probably the best one because it like the model to the left shows like some kind of correlation with the data, but it doesn't really catch the like the trends exactly, whereas the right one seems to catch pretty much every point, but
right.
maybe that's not super universal, so it wouldn't be
All right.
applicable to other data. And
Okay,
the middle one has the compromise between both.
all right. So that's a fair argument. Does anybody have anything against this argument, or does anybody want to say anything provocative? Andrea?
I will go for the one on the left.
The one on the left. All right, but why, if I may ask?
Well, there are some points that are very close, and they are very they are very close in the x-axis and very different in the y-axis that make me think the variance is such that there is noise in these points, and so the line on the left seems to average over these errors.
Yeah.
And while the one in the middle, it just tried to essentially interpolate the points, and this does not account for the inner stochastic error or that these points might have.
Yeah, I think that's a totally fair argument. And I think Luis has a hand raised. Please go for it.
Can't you just assume? Why would you assume that there are errors in the training data set? I would hope that the training data set was the best data we could get to train the model. So I'm going with the middle one being my preferred answer.
All right. Okay. That's again. Everything is fair. Kit, go for it.
If you put points in between, like if you imagine that you had an additional data, more data to add to the data set that was in between each of the points on the plot, then the middle line would go through the points that you added in the middle, whereas on the left and the right that wouldn't be the case. So left is underfitted, right is overfitted, and in the middle is probably what you want.
Again, totally fair argument. Does anybody here think that my question doesn't make any sense? Anybody feeling like that? It's a very weird question that I've asked. No. All right. There's too much respect for my question in this room. So what I really want to say,
Sorry. Maybe you could say that to give a good answer as to how well fit it is, like 10 data points is not enough. But I guess that's a limit more so the size of a PowerPoint than your question.
that is, yeah, I mean, definitely we can all agree that PowerPoint has many limits, not just the one pointed out right now. But I agree. But I think that touches upon many of the points that have been said touch upon. What I really wanted to highlight here is that the answer is there is no way of telling which of them is a better model, because we haven't really defined what exactly is a metric, and we haven't really defined the data set on which we would like to test it. So we only know how this model performs for these data points. We have no information currently on how this model does on the data that has not been used to train this model. And of course, I mean, now I'm going to show you this next slide where I'm going to add in more data. And turns out that the middle one actually is the best one. But actually there are good arguments to say, why the middle one was the most likely to be the best one. But in the absence of asking yourself, in the absence of really being provided with data course on fitting, where this scenario is called underfitting and this scenario is called overfitting. And the idea here is that in this case, your functional form is too simple. And again, this is just a case, and the reason why we can say that is because we know the blue points. For many cases, this would have been sufficient. But the point is that our functional form is too simple. Therefore, it really cannot capture the fluctuations of our data set. It just passes through all of them. So yes, I mean, this really is not an optimal model. On the other side, we have an extreme case where our curve passes through all of the data points. So if you really compute the residual error or the loss, the training loss that we have defined so far, this model would have the lowest loss. But actually, if we look at the other points which were not used to train this, fitting to all of those points makes this very wiggly. So by a small change in the value of your data, it leads to a very large change in this function. And in this case, since we don't really know what exactly what we don't really know about new data, one generally can make a reasonable assumption that the data that you're trying to learn on is sensible and it would be smooth, right? In that case, therefore, what you really want to go for is something optimal, that is a model which has the complexity to go through all the points, but it's not that complex. It's not that complex and not that fluctuating that if you try to interpolate between 2 points, you'll get something completely crazy. And I think all of these things were touched upon in the discussion that we had. Some of these, and again, overfitting is going to be a very big problem, because not just in theory, but in practice as well, because if we get data, suppose you're doing coupled cluster, I mean, each data point is so expensive, right? And we are really tempted to fit on everything and get the lowest possible errors, right? But that really may not be the best strategy here. In this case, you really don't want the model which gives you the lowest loss, and you really don't want to train on all the model that you have. Right? Okay. Now, some of these examples of overfitting are, again, these are not molecular modeling, or they are not even data science questions, but they just kind of give you a sense of, from the perspective of learning, what exactly is overfitting. For example, if somebody is leaving a company and you have to find a replacement, you set an advertisement for exactly the same, description of that person. And this really is a problem of overfitting, because you've taken what you had and you have not really said that well, and you have not left any wiggle room for what else could be a good candidate for this position. And then the other thing, which is more of a coincidence, is that if you sum the years where Brazil won these championship, you get this. And then again, if you sum up the numbers that where Germany won the championship, is exactly the same. And then there's one more. But of course, I mean, this cannot really be a universal model, right? Many a times, in the absence of limited data, in the presence of limited data, You could draw false conclusions. And just because based on the amount of data on which you perform your training, you're getting very low errors, doesn't mean that really is the best model. Okay. Again, I don't want to end here with a definitive answer on what exactly is the best model. And if somebody asks you that question, I think you should ask them the question, what is your criteria? And on what basis should I define what is the best model? And in all cases, I would say you really have to look at how well does the model do on the data that has not been used to train it. So you always need a so-called test or a validation set to judge how good your model is. Does anybody have any questions or comments here in general, or if there's anything people don't agree with or want to add something, go for it. Feel free to say anything provocative as well at this point. Nobody's going to stop you. Yeah, I see a hand. Okay, go for it.
When you decide at what point should you, what's the best point to decide whether your data is done in terms of when you train and you do various cycles, various epochs of learning, when should you decide to stop? How long should you train your model for before it overfits or underfits, or does the epoch number have anything to do with that? Or
Yeah, so that's a good question, and we'll deal with it precisely later on, but I want to give you an answer now. So the way that people really deal with this problem is that as soon as you have your data set, you split it into 3 parts. Of course, the 3 parts don't have to be the same size. The first part is your training set. The second part is your validation set. And the third part is your test set. And you're always supposed to fit on your training set, right? And when you perform your minimization and you look at your loss function, you need to also look at what is the loss on the data that has not been used to train the model. And when you have this situation of overfitting, you'll see that the training error would be low, but the validation error would be high. So at some point, you would reach a point where the error of fitting on the data set keeps reducing, but the error on the unseen data set will keep increasing. And that already gives you a cue. Yeah, you want to say something else? Go for it.
Have I just forgotten? Yeah, no, it's just slipped away from me. Sorry, I was still listening. Sorry.
Yeah, no worries at all. Yeah. All right. Okay, yeah. So the idea is to always split your data set, and even though you fit on one set of data, it's always good to look at what else, how your model does on data not used to.
I remember now. Sorry. If I have a set of ab initio data that I started with and I split that into, well, I use active learning to build a small and effective data set from the larger data set. If I didn't have a validation set independently of the initial data that I used to generate the model, would it, obviously because it's ab initio data, I can generate more to be the validation set at a later point? Is that still safe to do?
That is still safe to do, but if you generate, the devil lies in the detail here, that if you use exactly the same procedure to generate the validation as you did for your training, then it might be very similar, right? So you just have to find a way of getting more diversity in your set.
Yeah, I'm trying to minimize the amount of ab initio calculations that are performed because those are the most expensive.
Right. But I would still say that it always makes sense to just randomly select 10 or 20% of your data and not train on it. You won't gain much.
Okay.
And in the sense, you won't gain much on accuracy, but you will gain a lot more on understanding how good your model is. Right.
Yeah.
But we'll actually tackle these in more detail later on.
Okay. Yeah. Thanks.
Okay, so this is next. Do you have a comment here?
Yeah, I just had a question.
Right.
My connection's a bit unstable, so maybe you just answered it to Kit. But
No worries.
I was just wondering how, so like data augmentation with it, I'm just kind of curious as to how you go about augmenting these potentials and like input and output data, considering you get them from these ab initio models.
Right.
Or do you even do data augmentation for atomic potential learning?
So how about, so this is going to be the second part of because I wanted to start off with just a description of the basics of machine learning to get everybody at the same platform. But these more specific questions I'm going to tackle later on. Is that okay if we wait until then?
Yeah, that's fine.
Yeah. All right. So yeah, maybe we can tackle this later. All right. Yeah, but thanks for the question. Keep asking or keep interrupting. All right. Okay, so let's just sum up what we have learned until now. So first, the limitations of physical models. And again, I mean, these limitations are only, we are discussing them because, we want to apply them on cases where they have not been trained on. But by no means I'm trying to make, arguments that physical models are worse than machine learning models or vice versa. But again, from what we have discovered, from what we have discussed, what are the limitations of physical models? Can anybody answer? At some point, I'm going to start taking names randomly, just to get more involvement. How about Dimriti Lapshin? Sorry if I'm mispronouncing your name. Do you want to answer this?
Well, maybe the limitations of physical models is that they kind of have the same, well, let's say if we take a particular model of water, let's say T4P, it's calculated, I think, like based on a particular set of data, and essentially, therefore, you can use this model for specific, in order to learn a particular property of water. Some models better reproduce vapor-liquid equilibria. Other models better reproduce properties of ice, but you cannot have a universal model using, I think, this.
Yeah, I think that's a fair point, and maybe I can sum it up briefly by saying that a physical model would be limited by its functional form, and sometimes a limited functional form will give you a very good property, but it's possible that it won't model another property very well. And does anybody have any other point on what other limitation could we have here? Maybe I'll extract one more point from what Dimriti said, which is also about transferability of your model, and that's related to your functional form, that you could train it on one system, but then it's not necessary that it could give you the same level of accuracy on a slightly different system that you have used. Right? And the third thing that I would like to say, and then we can move on, is that it really is very sensitive to the thermodynamic data that you have. So some cases you won't have much data, in other cases you would have, So that kind of makes it not very secular in terms of what you could model. All right. I had some rules of thumbs for data-driven models, but maybe we don't need to get into it. Maybe you're all interested in machine learning potential. So yeah, let's just go towards machine learning potential. I think there'll be more questions there. All right, so data-driven modeling, the idea here is that you solve the Schrodinger's equation, which is, or you try to solve a Schrodinger's equation, or you try to bypass solving the Schrodinger equation using, say, density constant theory. But the main goal that you have is that you have your input, which is defined by the positions of your atoms, and then you have your output, which is your Born-Oppenheimer potential energy. your goal is to find a mapping between the input and output. So this is exactly like the kind of problem we dealt with, where we had some input data and some output data, and we want to find a function which represents the same. And the idea is exactly the same here, right? So of course, I mean, one way of doing it is to actually say, well, for every position, I'm going to do some strenuous theory and computation. And with that, I'm going to get my energy eigenvalues. And the other way would be to just say that, well, let's go completely agnostic and try to just take a bunch of data points and see what we can do in terms of a prediction. Now, why is this approach going to be helpful? Well, because it would have a much lower computational, excuse me, it would have a much lower computational cost than directly solving the Schrodinger's equation. Then secondly, at least what we would like to have from this model is that it would be cheap and it would be fast to train as well. You would like to have a framework which is easy to validate. As you will see later, these models will be transferable to some extent, depending again on a bit of craft work. Importantly, they should be systematically improvable. The more data you add, the better this model should become, at least in principle. It should have a favorable scaling with system size. Now, we know that electronic structure methods can scale with polynomial or in some cases even exponential of your number of degrees of freedom. Of course, you can make them linear, but what if your model was linear to begin with, right? That would be really great to treat much larger system sizes. And finally, what you need is a good implementation. It should be able to scale on supercomputers and so on, right? Okay, so the basics of machine learning potentials are featureization and localization, right? So these are the two main things. If you understand what are these features and what does this locality of the model means, then you would really be able to understand, at least in my opinion, that would really allow you to understand what's going on with these. Okay, so of course, in the end, you would be using these as black boxes, right? But it would be useful to go inside this black box and really see what we do and how do we go from the structure or position of nuclei to the energies, all the forces acting on individual atoms, as well as the stress or the pressure acting inside the box where you've placed all your atoms, all right? Now, the rest of this section will be split into two parts. The first part will be featureization, which is how do you take this data and you transform it into a form which is easier to learn. And the next part will be on how do you fit the model, right? So the first part again would be just pre-processing the data. And the second part would be what exactly is the functional form that you're going to use to represent your total energy. All right. And let me tell you that this bit is extremely important, not just for machine learning potential, but in general towards understanding other old potential energy families as well, like your embedded atom model and so on. All right. So we are going to take the classic case of Bell-Pinello neural network framework, and extremely sorry for people who wanted to go for more advanced architectures. I have one slide where I'll touch upon those, and maybe that will give you some hints on what to look at, or maybe you already know that. Yeah. But the reason I'm going to focus on Bell-Pinello neural networks is because I really can explain all the aspects of this model. Okay. So the idea here is the following, that you take your input data, which is basically a set of all the positions of all the atoms in your system, and then you transform it using so-called symmetry functions. And what these symmetry functions do, I'll again dwell on this a bit more later on. But all you're doing is that you're kind of looking at histograms. Here, you transform your input data into a set of symmetry functions. And for each atom, you compute all of these symmetry functions, right? So for example, GH1, GH2 up to GHN are the values of the symmetry functions for all are the values of all the symmetry functions for a given hydrogen atom. Okay, and then in this case you have G0, GO1, GO2 up to GON. These are the symmetry functions for the oxygen atoms. So the idea is you take your data, which could be 3n dimensional, and for each hydrogen atom, you come up with a set of a vector of dimensionality n, where each element of this vector is this function, which is the symmetry function, and you do the same for the oxygen. They don't really have to be of the same dimensionality. Okay, and after that you train a separate model for the hydrogens, and you train a separate model for the oxygens. And with these models, what you predict is the energy of a hydrogen atom. So at the end, what you have is the energy of each hydrogen atom, and then you have your total energy. All right. So this part of it is called featureization, while this part is your local model that you consider. All right. Okay, so what exactly is featureization here? Well, the idea is simple. Let's say that you have a data set where each data point is the nuclear degrees of freedom of a water molecule. So that's 2 hydrogen, 1 oxygen. That's a 9-dimensional vector, right? Okay. So in this case, what I've really done is that I have taken this, I've taken 5 configurations of water molecules, and all of these positions are different, and I have computed the potential energies. And let's say we want to learn on this. Now, the only reason I've done this is because I just want to show you that you will be dealing with situations where a lot of configurations will have exactly the same energy. And in this case, all that I've done is that I've randomly translated and rotated the water molecules, and that doesn't change the potential energy, right? Now, if you were to feed this to the model directly, you will have to provide a lot of data where you show this kind of degeneracy, where you show that, okay, if I translate my atoms, the potential energy will not change. And at the end, you're asking your model to learn a constant function. And that is a little redundant. Yeah. Now, the other thing that you can do instead is that instead of providing to your model the raw positions, you can provide the distances, right? So you can provide the distance from the oxygen atom. So for the oxygen, that would be 0. For the first hydrogen, it would be 1.0. And for the second oxygen, it would be 1.1, right? And already by transforming your raw position into distances, we've achieved some sort of simplicity where at least this is automatically invariant to translations and rotations. So to our model, we won't really expect it to learn basic symmetries like translation and rotation. Our data will already take care of that, right? So the idea behind featureization is to apply as many symmetries of the system as you know. And in this case, for example, going from your raw positions to distances kind of makes it invariant to translations and rotations. Okay, now we take the second case of representing data. Let's say I show you these 9 components, right? And in this case, all I do in the second case is that I have just changed the labeling of my hydrogen atoms. In the first case, this hydrogen was named 1. In the second case, this was named 2. And of course, my input has once again changed, right? If you look at the distances, even the distance vector has changed, right? Because now the distance between the first hydrogen and oxygen is 1.1, and for the second one, it's 1.0. Again, you don't want your model to change, when you flip, you make these kinds of permutations or flips, right? And in this case, again, we have an issue that the potential energy is exactly the same because all you've done is flipped your atoms. So how can you make sure that how do you transform this into something which will not change once you change your atoms or once you perform this permutation? And one way of thinking about it is that, well, instead of taking distances, how about I take sums of distances? For example, I just add all of these up. And in that case, that would give you one feature, and that wouldn't change, if you permute your atoms, right? So this is just to give you some sort of understanding that by working in terms of distances and by taking summations of functions of distances, we could actually eliminate the translations, rotations, and permutation degrees of freedom which can actually change your data, but it will not change your potential energy. All right. So long story short, the idea is that you take your positions and you transform it into certain functions, which will not change if you translate your atoms, if you rotate your atoms, or if you just flip the indices of your atoms. Right? And this is exactly what symmetry functions do. For example, this is the functional form of a so-called radial symmetry function. And this has this particular functional form where you need to compute it for a given central atom, right? So if you sit on an atom and you compute this radial symmetry function, and if that function looks like this blue curve, then essentially what you're trying to learn here is roughly what is exactly is the number of atoms which are at a distance of around 1 or between 1 and 2 angstrom. So this is what the symmetry function gives you, right? Again, the symmetry function is based purely on distances. And at the end, you have this Gaussian function on top of that, and you have a summation. So this is going to be invariant to any rotation, translation, or permutation. All right. Now, then there is another set of symmetry functions called your angular symmetry functions. Okay. Now, what these angular symmetry functions will measure is that for a given atom, you have to create, for a given atom, you have to ask, well, if I take pairs of atoms, approximately at what angle are they present at? And for example, this particular dark red will tell you that, okay, if you have taken a pair of atoms, then what exactly is the number of atoms which are 180 degrees from this line? Or for example, this one will tell you how many atoms are there at this particular angle, right? So basically, by computing these radial and angular symmetry functions, what you end up with is for each atom, it gives you a probe of its neighbors, right? And it tells you basically how many atoms are there at 1 angstrom, or how many of them are at 2 angstrom, how many of them are at 3, and so on, or how many pairs of atoms are at a given angle, and so on. Okay, so these are called radial symmetry functions, and these are called angular symmetry functions. The other thing that you will note is that all of these are multiplied by this cutoff function. And all this does is that this just makes sure that all of these smoothly go to a 0 up to after a given cutoff, in both the cases. Now, does anybody want to answer why do you think we use a cutoff function? Or does anybody have any questions about these symmetry functions? Yes, Kate, go for it.
I may not be relevant, but so what happens if you were to apply something like a uniform electric field?
Right.
And then you needed some kind of directionality to your neural network so that it would know where it was relevant to the field. I presume that these invariant symmetry functions wouldn't be able to do that.
No, in that case, it won't work. And you can ask yourself the question, why? And in that case, the answer is, if you apply an external field, then your total energy is not invariant to translations. And it's also not invariant to rotations, right? But it will still be invariant to permutations, right?
Yeah.
Therefore, the kind of features that you would like to choose in those cases would be those which which are not invariant to translation or rotations, but they are still invariant to permutations. So depending on the symmetry of what you want to learn, you need to select your features.
And would I think an equivariant type network would be able to incorporate those things. Is that true?
Not really, because actually the equivariant network is extremely similar to the Bell-PI-NLO neural network scheme is almost as sophisticated as most of the other schemes. The only problem here is that we only consider functions which measure triplets of atoms,
Yeah.
While in an equivariant network, the advantage you get is that you can have n-body correlations as well if you want to.
Yeah. Okay. Fair enough.
That is the only thing.
Do they
Yeah.
do they have cutoff functions in equivariant networks as well?
Oh yeah.
Yeah. Okay. And do you converge? And when one uses these types of networks, should you converge your cutoff function? So try many different values and see when the energy is stable, or how would
Yes,
you
you should
decide?
always. The cutoff function would be a so-called hyperparameter. So yes, I mean, on your validation set, you should see, what is the effect of changing the cutoff.
Would it not impact the training? Yeah, it would impact training too.
I would say the error on the training set is less important as long as it's not some crazy number.
Okay, cool. So you can converge your cutoff after you've done your training and check that everything's okay.
Yes, you can fit various models with different cutoffs and compare them on the validation set on the data that has not been used to train.
Yeah. Okay. Thank you.
Okay. But Kit, can I ask you a question?
Yes, of course.
Why do you think we use a cutoff?
Computational time. As the radius increases, the number of pairs increases as well, and it just becomes unfeasible to have a have the number of symmetry. So you've got loads of different symmetry functions here centered at different distances. As your cutoff function increases in size, you'd need more symmetry functions. You'd have to evaluate all of those. You'd have more pairs because there are more pairs of atoms and more triplets inside the radius as well.
So that's a good point. So basically, one of the reasons for using a cutoff is that if you use a very large cutoff, computing all of these features will get extremely expensive.
Yeah.
So the number of combinations of atoms is going to keep increasing, and that will increase the computation cost, right? So that's one of the reasons. Yeah. So yeah, but there are more reasons, and we'll get to those in a little bit. Why do you think we use smooth cutoffs and exponentials? For example, you can see that this is a Gaussian, right? And what you are really measuring here, probing here, is the number of atoms in this region, but you've basically widened it. So why do people think that we need to use an exponential here, or why do you need to forcibly make sure that this goes to 0? So I was going to ask the question, why should we use smooth cutoffs on exponentials? And I was going to ask if people here have used the Leonard-Jones potential and so on. And does anybody have an answer for that?
I think I see two reasons. One is for doing derivatives without discontinuities, and the other one is that if you are doing a dynamic set, at some point you have an atom falling inside the cutoff, you don't want that, like the optimization, the parameters could become unstable with a sharp cutoff.
Right. Yeah, I think these are fair points, and Andrea is absolutely right. The first point is that you want your we know a few things about the potential energy surfaces. We know that they are smooth positions, so a small change in the position generally leads to a small change in the energy. So we have to enforce some sort of smoothness into our function, and the way we can do that is by using these. Let's say this is more like a Gaussian convolution of your histograms, right, with some widening. And that really makes sure that your symmetry functions don't change very rapidly when your atoms move. And the other thing, of course, is computing derivatives. If an atom is within a cutoff and after displacing it goes outside, there will be a sudden change in its value, and that would lead to a very large force or a very large pressure on your system. And these are some of the reasons where you would like to use smoothed functions instead of delta functions. All right. Okay. So what kind of information are we missing in this representation? So we have basically decided, okay, I'm going to sit on every atom and I'm going to count how many atoms are there at a distance of 1, 2, 3, 4, up to, let's say, my cutoff between some intervals. And then I'm also going to look at, for example, if I sit on a particular hydrogen, I'm also going to look at what angle is our oxygens and hydrogens at a particular distance from this. Now, what kind of information are we missing here? Anybody wants to answer this? Kit, yeah, go for it.
All terms above 3 body terms.
Yes, so that's you've thank you. You have destroyed the suspense completely. Yes, but yeah, I mean, basically what we're trying to do here is build an n-body correlation function. So yes, at the end of the day, you are going to use these 3 body terms and you're going to make nonlinear functions out of these 3 body terms. So you could get a 4 body function out of these, but you can always find certain 4 body functions which you will never be able to define. Now, the good news is that for a lot of cases, you don't need to go beyond, let's say, pairs of atoms, and actually, this is interesting. Before these n-body correlation functions or n-equip or NICE, all of these potentials came about, people were really convinced that you don't need anything beyond 3-body correlation, and they were convinced even that any potential energy surface would be describable in terms of 3-body correlation functions. But yes, you can find corner cases where it doesn't work. But most of the information is already encoded in these, is what I want to say. Right. Now, there's one more thing here, which is that it's this very nice paper on the nearsightedness on electronic matter, which kind of motivates all of this featureization as well. That changes of the potential, no matter how large, beyond a certain radius, have limited effects on the local properties, right? Now, in this case, as you'll see later on, you're not trying to ask, how will the total energy of my system change if I move atoms? What you're really asking is, if I sit on a particular atom, how will the energy or the force acting on this, atom will change, And based on this nearsightedness of principle by Walter Kohn, anything beyond a sufficiently large cutoff is going to have very limited effect. And basically, the more you increase your distance, the less the impact will be. Therefore, it kind of makes sense, to use this so-called local feature around a given atom, because at the end of the day, we will benefit from this nearsightedness of our electronic properties. And because of that, the atoms which will have the most amount of impact on the electronic energy, particular atom will be its neighbors. All right. Now, again, I've told you what these features are. I really want to explain exactly how you're going to regress. So I want to give an example. Let's say you have an aqueous system, and let us say that you want to compute these symmetry functions for one hydrogen atom. Okay. Now, in this case, let's say that you are going to choose these symmetry functions. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So basically, you have your hydrogen atom, which is a 3-dimensional function. What you're going to do is that you're going to make a 19-dimensional function from this, right? And the way you're going to do that is by computing these symmetry functions. So the first component of this 19-dimensional function is roughly going to look at how many atoms are there around 1.5 angstrom. The second component will look at how many atoms are there at around 2.5, then 3.5, 3, 4, and so on up to your cutoff, right? Now, the other thing you should notice is that now this symmetry function is only going to look for the hydrogens which are at around this distance, right? So now you've got this other set of symmetry functions which will look at how many oxygens are there approximately in this region of around 2 angstrom from my hydrogen, and how many of them are at around 3, right? And then you would go to angular symmetry function, where if you sit on one of the hydrogens, then you will ask, for a given distance, let's say 1 angstrom, what kind of angles do these other O and H form with respect to my central atom? And based on that, from just the position of one atom, you're going to define a 19-dimensional vector that gives you a sense of the local environment of this hydrogen atom. And the way you give a sense of this local environment is by doing these rough histograms, by counting, how many atoms are around this particular central atom at these distances or along these directions and so on, right? Now, you will notice that if I double the system size, and I sit on this hydrogen, the only atoms that will contribute to these symmetry functions would be the ones in the cutoff. And even if I double the system size for a given hydrogen atom, the dimensionality of the feature would still be 19, right? So basically, by using these features, we have made the dimensionality of the environment of an atom independent of the dimensionality of the system. I want to ask you all, what do you think? Do you think there are any advantages of this or not? Yes, Nick, you have your hand raised.
I had a question, but as to
Yes,
the
go for it.
advantages, I guess it means that you can treat larger systems without requiring any more computational, well, as much more, you wouldn't need as much more computational resources for a larger system.
Why is that?
So actually, no, you would need more computational resources, but you would be able to use the same machine learning model because the input dimensionality is still the same.
Yeah, so that's a good point. So you're talking about, this is called size extensivity, where you basically say that you can use the same model even if you make the system size double, you would still be able to use this model. And that's precisely because for a given hydrogen, it doesn't matter, which atoms are beyond a certain cutoff, right? So even if you have twice the number of total degrees of freedom for that particular hydrogen, you would still have the same number of degrees of freedom contributing to these. And then you would have exactly the same set of vectors describing the environment. So one can argue that this kind of a description makes your machine learning model transferable. Because if you have a water molecule in bulk, or if you have a water molecule in a protein, you could still ask the same question. You could still describe the chemical environment of your water molecule by asking the same questions. How many other hydrogens are there at a given distance? Or how many other oxygens are there at a given distance? Of course, if you use proteins, you'll also have to ask questions like how many nitrogen atoms are there, right? And if you use those symmetry functions, those values will be 0 for water. But at least by using these and by using this set of descriptors, which have a fixed dimensionality, you can apply the same criteria to any system. And you can ask questions like, if the local environment of my central hydrogen atom changes, by how much will its energy change? So these are some of the advantages of using these symmetry functions. Yes, so then there's the question, how do you select them, and how does the number of symmetry functions scale with the number of atom types? Now, I'll basically answer this question. There is no systematic way of selecting these symmetry function, and there is a bit of empiricism involved. So you really need to ask questions like, at 1.5, what exactly is going to be the number of atoms, or at a given angle. Now, you may know for certain systems which distances or which angles are more relevant, and it's useful to use that information. However, actually, it's also not that difficult. For example, if you just say that, well, I'm going to use a cutoff of 6 angstrom, and you just start placing these Gaussians with uniform spacing, and again, you start placing these Gaussians at angles, and just systematically start widening them. Generally, that is sufficient to give a very good description of your local environment. And the other thing about how does it scale with the number of atom types? Does anybody want to answer that? Anybody who hasn't answered yet? Nick, I know that you're unmuted, but maybe I'll ask somebody else, if you don't mind.
Oh yeah, sorry, I just forgot to mute myself again after answering the previous one.
Right. Anybody else? Marco. Sorry, I'm now taking random names. If you are there, do you want to answer this question? Well, anybody else?
You'd have to make the model have more dimensions if you had more atom types.
Exactly. Yes. Yes. So I guess my question was, for example, if we have two atom types and we use pairs and triplets, versus if we have 5 atom types, then by how much is like what exactly would be the scaling behavior of the dimensionality that you'd have to deal with? That's basically.
Would it be 2 to the 4?
Yes, I mean, so we'll have some sort of an exponential like scaling because we would have to form all sorts of combinations of atoms, right? So in this case, with oxygen and hydrogen, we just have pairs of hydrogens, pairs of oxygens, right? But if we have 5 different, so we'll have more pairs, and then we'll have much more triplets, right? So the cost of making these features will keep getting larger for more atom types. And again, for those who are interested in more advanced models like NEQUIP and so on, they have exactly the same problems. There is no way to get around this rigorously, at least right now. The more atom types you have, the more will be the cost of these models. But again, I mean, studies have shown that up to 5 or 6 degrees of freedom, you can get these models to work rather efficiently. Yes, Nick?
Sorry, so just like that question I had, I guess is kind of related to this. Like I can see the advantages of using these symmetry functions because it can simplify the data. You can put in the symmetries already, but then as you get more complicated systems, is there maybe some advantage to just using the atomic positions? And has anyone done that, or does it just give you terrible outputs?
Yeah, I think that's a very valid question to ask. It's like the elephant in the room. Why are we doing all of that? And to answer your question, I only know of some unpublished work very recently done where they have tried to address this question using much more complicated architecture. So again, there are 2 limits. Either you use very simple data and very complicated models, right? Or you complicate your data and use simple models. With Bella Pinello, what we're trying to do is something in between where we slightly complicate, our features, and then we use a slightly complicated model, But if you want to just use positions, you'll have to use a very, very complicated architecture. And currently, I don't think anything works out of the box, unfortunately. But yes, eventually it would be great to just feed in some positions and get energies out. Yeah. Does anybody have a question, or do you want to ask something else?
Venkat, one question. So in here, when you have 2 molecules that are beyond the cutoff, they essentially interaction. And so if the cutoff is the order of 5 angstrom, that means like you wouldn't feel the Coulomb even when it is important. And of course, if you have something like a liquid or a solid, where some closer than that, you can, I mean, in a way, correct for this missing long range, because you can mediate with the, I guess, with the molecules that are in between. But is there any paper or work that show up to which point this issue of missing Coulomb and Van der Waals, missing the long range, is solved, and when it is not?
Yeah. So far, what we know about this is that actually using a baseline of electrostatics and then for everything else using machine learning works very well, actually. So it has been found that for very heterogeneous systems like liquid vapor interfaces, these cutoff based models can give you a poor description of the local structure. And therefore, in those cases, using, let's say, just Coulomb interactions for point charges between oxygen and hydrogens, and then everything else, you subtract that, and everything else you train a model to it, that seems to work very well. The cases where it can fail dramatically is if you just suddenly you change the oxidation number, due to a chemical reaction or something. But those are, you can construct cases where this would not work. But so far, it looks like it seems to work rather well. All right, I think maybe I can move on to the model part of the Bella-Pinello scheme, where up until now, we know that if you take your positions and you construct these abstract vectors, which for each atom tell you what is the chemical environment of the system. And the way the chemical environment is probed by asking how many atoms of a particular type are there in this particular cutoff, how many atoms of particular type are there in another cutoff, and so on, or how many pairs of atoms are there at particular angles and distances, and so on. And you have to construct these vectors for all the atoms in your system. And then you have the next part where you take these and you try to regress the total energy of the system. But again, you don't do it on the total energy, actually. The way people have done this, and this is again taking inspiration from these EAM models, which compute atomic energies. Even in Bella-Pinello, or in actually all of the machine learning potentials, you always predict the atomic energy, and then you sum all the atomic energies, and that gives you the total energy. Right. So yes, so this is something like that. So the total energy at the end would be the energy of all the hydrogens and the energies of all the oxygens. So your code, the code which actually fits your Bella-Pinello model, that will basically fit two models, one for the hydrogens and one for the oxygens, right? As an input, it will take the environment of a particular hydrogen atom and predict the atomic energy. And then you will sum that over all the hydrogens. That will give you the total energy of all the hydrogens. And this will give you the total energies of all the oxygens, right? And the sum of all of this determines the total energy of the system. Now, clearly, I mean, this local construction has been performed for a reason, and we can ask what exactly are the advantages of this local construction. And I'm just listing some of these here. The first one is that we know that in the large, at least in the limit of large system sizes, the energy is an extensive quantity. It's a thermodynamic quantity. And if you double the amount of iron, its energy will also double, right? So this construction clearly allows you to have those kinds of properties. The other thing is size extensivity, which is that if you train your model on a small system and you predict the energy of a much larger system, you would still be able to do that, because in the large system, if you just double the system size, your atoms will have the same environment, And again, all you will have to do is that just ask, what is the energy of each atom? And you can just sum over 4 times the number of atoms if you just, extend your system along X and Y, or 8 times if you just double each degree of freedom. And finally, by making these models a sum of local energies, you have already a linear scaling with the system size. So that's extremely advantageous. So there's no additional computational cost. Now, some of you may ask, don't you have to compute pairs of atoms or triplets of atoms, right? Shouldn't that be n squared or a higher degree? But actually, those you always compute up to a cutoff. Therefore, the scaling still remains linear. So roughly, you could argue that the number of neighbors of a particular atom will always remain the same. Therefore, the cost will not change by that much, right? So you would always have a linear scaling with cost. And finally, the most important reason why this should work is the nearsightedness principle by Walter Kohn, that actually the density matrix of a particular atom will always reduce exponentially with distance. Therefore, beyond a certain point in space, it will have a weakening effect on the electronic properties of the system. Therefore, that kind of motivates the use of these local models. Now, what are the disadvantages of this construction? Well, the first one is that it is a purely short-range model, and I think Andrea talked about the limitations of of not being able to capture non-local interactions, or something like electrostatics, which is actually infinitely ranged, right? Yes. So those are clear disadvantages, and many people are working on non-local machine learning models, or many people are working on including electrostatics into these models so that they can be applied to very large systems, or they can be applied to extremely heterogeneous systems like liquid vapor or solid liquid interfaces, which have very different environments on both sides, right? All right, so this sums up the model part of Bell-Pinello models, right? So again, just to sum it up, instead of regressing the total energy of the system by a single model, it is useful to regress the individual atomic energies of different atom types, and then predict local energy. Helps with transferability of your model as well, because again, if a protein has an environment, where up to a cutoff, a hydrogen atom only has hydrogen and oxygen atoms, which means it has a water environment around it, you would still be able to use the same model to predict its energy, right? So it kind of helps you with transferability. And then it also allows you to have a linear cost, because the total energy is sum of individual atomic energies, order n. And finally, energy will remain an extensive quantity. Does anybody have any question about the model part of Bell-Pinello?
Venkat, can you say something on the neural networks that are used here? So what kind, how deep they are?
Sorry?
Can you say something on the neural network that are used for the training? So
right, you mean the architecture of the neural network
yes.
that I use? Right. Okay. So I will actually Bell-Pinello scheme uses like one of the simplest neural network. It's basically an artificial neural network which has 2 to 3 hidden layers in practice. So it's really the simplest neural network that you could use. Yes. There are other models like SNET, which uses a convolutional graph neural network. Then DeepMD, uses a number of layers of convolutional neural networks, and so on. But I don't think all of those provide you with a very large improvement over the Bell-Pinello network. In fact, for example, the gap potential instead of neural networks uses a kernelized model as well, and that also works really well, right? So once you have done your symmetrization and featureization properly, you don't need a very complicated model. Anybody else has any question? Nick?
Yeah, I feel like maybe I missed it, but does something like the temperature come into this only at the level of when you make your initial data set, and then after that, right, the network is trained for that temperature only?
Excuse me. Not necessarily, and that the devil lies in the details of your training set, and that's the next thing that I'm going to discuss: training and validation. Yes, so I'll touch upon that. All right. Maybe that's a cue that I should move on. Okay. So the next bit is actually training and validating your model. And the idea here is that you take your generally, in most cases, you have to train in an iterative manner, because it's very hard to get a data set which has all the required complexity, to represent all the environments that you would like to see in an application. So the basic idea is that you take a bunch of points and you train a very preliminary model on that, and after that you get a preliminary potential, then you run more simulations, then you run some simulations, get more data out of that model, you perform your validation, and if you see that the errors are very high, you take some of those additional points, you perform more first principles calculations, you again perform your training, and so on. So this cycle keeps going until you are satisfied with your model, right? So, I mean, there are many ways of creating your initial data set. And for example, you could use some force fields to get, let's say, a few hundred configurations. There might be an online database already. There are many people working on systems, and on Materials Cloud, you are likely to find a lot of data. You could use tight binding or semi-empirical density, semi-empirical models, like density functional tight binding, to come up with your initial data set. You could use density functional theory with unconverged parameters, just to get something, or just first principles random structure search. So you name it. So there's no real scheme here, to come up with your initial data set. But the idea is that just get something, train something, and then you have something to work around with, right? Now, the next bit is how do you validate your system and or your model? And the idea is that as soon as you have your data set, you should always split it into a training set and a test set, and that will really help you during your validation step. So whenever you model your validation, whenever you do your error analysis as a function of number of optimization iterations, you should always simultaneously plot the test and the training error. And the reason for that is it will allow you to understand the onset of overfitting. Now, when your training set error starts decreasing at the cost of an increase in your test set error, that definitely means that your model is too wiggly. And if you have a new data point, that is more likely to give you a wrong result. So basically, in your test set error, you will find this minimum, and that minimum is exactly the point where you should stop. At that point, up until that point, optimizing more leads to a reduction in error. Beyond that, it makes your model worse, right? So this is where you should stop to prevent overfitting. And this is also called early stopping, for instance. Now, the other thing about, for example, the question was asked, if you train, your model at a given temperature, is it only going to be valid at that temperature, or can you use it on a different temperature? Well, I would say that it really depends on what kind of sampling you have performed. If you perform your sampling at high temperatures, then you're likely to have a more diverse set of local environments in your training data, and therefore performing simulation at lower temperature should also help. But if you perform your data set, calculate your data set from low temperature simulations, you're likely to miss out on a lot of possible configurations. So it's always helpful to go with to get your data set at more extreme conditions and so on. Right. Now, this is again related to this particular plot that I'm showing you, which shows, this is meant to show you that the error in your the error of your machine learning model is very different in the regimes of interpolation and extrapolation, right? Now, and this is going to be extremely useful in how you develop your training set. For example, let's say that your initial data set allows you to perform a molecular dynamic simulation. Now, at that point, when you perform your training, it's useful to, instead of training one model, it is useful to train an ensemble of models, let's say 4 models, okay? Now, and it's useful to predict these models on your entire set. Now, what you will see is that for the data which is in the training set, most of your models will give you very low discrepancies, while for the data which is not in your training set, the models will give you very different results. And this is basically because when you extrapolate, the neural networks can actually give you a very big divergence, and that allows you to select your data points carefully. And this is a big advantage, because if for a particular data point, the disagreement between your models is very large, that means you should most likely be adding that point to your training set, right? So basically, you perform your validation, you see that all the models disagree very much for this configuration, then you perform a reference calculation for that set. Now, next, you will see that for that training point, the errors of your model will be small, but for certain other points, the errors will still be large. Now, that's your cue that you should probably add this, to your training set. Now, if you perform this kind of a step, if you perform this kind of a scheme, then you will be able to add only those points to your training set which are already not present, and this will avoid redundancy. it will allow you to have a small and compact training set. And of course, given that you predict with more than one models, it will also allow you to understand how good is your model at extrapolating. All right. And this was basically the bit on training and validation. So just to repeat myself, the basic strategy is to take an initial data set, train a preliminary model. Then with your preliminary potential, you perform some simulations. For those simulations, you predict using multiple models. You monitor whether they disagree with each other or they agree. If the configuration on which the models are giving very similar results, that means that that point is already in your training set. If not, and your system has not exploded completely, you should definitely add that point to your training set and so on. And you can keep doing this, keep increasing, let's say, your temperatures and pressures until you get most of the representative configurations in your training set. Yes, Savir, do you want to ask a question?
Yeah, so I see in this example that you've done different models with like different neural network models. Would it also work if you did like different, like kernelized model and a neural network model in this stage? Okay.
Yes, so as long as your model has a lot of parameters, and both kernel models and neural networks are in this regime where the number of parameters are much larger than the amount of data. In that case, in the absence of data, they are likely to give you very fluctuating results. Yes. In fact, this kind of a scheme is related to like a very rigorous uncertainty estimation scheme, and you can show that the disagreement between your models, trained on different parts of the data, actually is rigorously related to the true error of your system. So what I really want to say here in this next slide about uncertainty estimation is that generally, instead of training one model, it always makes sense, to train multiple models. For example, if this is your training data and that's your test data, then it is always useful to not train your model on the full training data, but to randomly sample, a percentage of points from your training set, and then train an ensemble of model on different sub-sampling of your training set. And you can make sure that the final prediction is the mean of all of these models. And the standard deviation of these predictions actually is related to the uncertainty or the error of your model. And using these uncertainty-related schemes or these committee-based schemes, where instead of training one model, you train an ensemble of models, you can actually make rigorous error predictions and, let's say, add error bars to your profiles. For example, here there is a free energy profile for a reaction computed using a machine learning potential. And you are actually able to propagate your errors, onto your free energy profile. And this is done by simply training multiple models, running multiple simulations, and looking at the disagreement in your free energy. Yes, Savir, you've raised your hand. Go on.
Yeah, I was going to ask, so is there a limit to how many models you should include in this ensemble? Because surely if you have too many of them, then you will reduce your data. You will reduce the data points at which point it might not, your final model might not make sense.
Yes, so it's not necessary that the data set that model 2 and model 3 use are completely distinct. So in principle, you could just randomly select a fraction, of the data set. And actually, in that limit, the more models you do, the better is going to be your prediction, and better is going to be your uncertainty prediction. So the answer is there is no limit. The best case scenario is to make infinite models, but the practical answer is that the more models you develop, the more costly it will be. So as a rule of thumb, it should be greater than 4, and generally 8 models or 6 models is a good enough number.
Okay, thank you.
All right. Okay, and at this point, I'm going to summarize everything about the Bello-Pinello neural network scheme. So the idea in the Bello-Pinello scheme is that you take your initial inputs and you transform them into a set of so-called features, and what these features do is that they sit on a particular atom and they describe its chemical environment on the basis of these histogram-like functions. So the chemical environment of a particular atom is described by how the other atoms around it are placed, at what distances, at what angles, etc. they are located, or their pairs are located. With that, instead of a vector with all the positions, you have a vector for each atom, and this vector actually is a set of these features. So you do a transformation of your position into a set of vectors, which have a dimensionality that doesn't depend on the dimensionality of the system. And then what you do is that instead of predicting the total energy, you predict the energy of each atom on the basis of its descriptor, and the total energy is basically the energy of the individual atoms. For the models that predict the energy of a particular atom, you can use neural networks, you can use kernel models, and actually the more recent models even use linear regression to get to regress your total energies. And again, as long as your features are complicated enough, it doesn't matter even if you do linear regression. You'll basically get the same results. Now, finally, your energy is a sum of the local energies that will allow you to take derivatives like the forces, which will be like the sum of all the forces, or the total force will be the sum of force acting on all the atoms. And if you take the derivative of this with respect to the volume, you will also get your stress tensor. So with that, you will be provided with energy, forces, and stresses, which can be used to perform molecular dynamics or path integral molecular dynamics simulations, right? All right, so finally, I hope I was able to give you a description of exactly how these machine learning potentials work. And I was also able to convince you that they are much cheaper than ab initio potentials. They are not very hard to validate. Basically, if you have your total data set, all you have to do is separate it into a test and a training set, and only train on the training set and validate and check your errors on the test set. Basically, you need to test your model on the data that has not been used to develop it. That's a good test on how good a model is. Now, because of the local description and these symmetry functions, it should be possible to transfer this model from one system to the other. Since these are all universal approximators, adding more data should in principle lead to an improvement in the accuracy. Because of the local description, there is a favorable scaling with system size. Very good implementations are available, like N2P2 and so on. I'll be sending an email with more resources on that. And they are cheap and fast to train. Now, it's important to know what are the sources of error in these machine learning models. And the first error comes from the locality assumption that everything is short-ranged, and everything is additive. Now, there are many forms of potentials which are actually non-additive, and van der Waals interactions are the best example of that. So, but in this case, we do assume that that all your individual energy components can be added just like that. So these could be sources of error. Generally, lack of training data or overfitting to limited data is a big source of error, which means that there is some remnant error in your fitting. And the third thing is when you transform your data into your features or your symmetry functions, if you have not sampled your distances and angles properly, or if your system is such that it requires 4-body or 5-body correlations, which admittedly is rare, then you will have some sources of error. Well, I mean, for those of you who are interested in much more complicated models, I mean, I want to show you this slide, where this is just a tree which allows you to, which shows you that it's possible to create the full family of all the machine learning potentials from just Cartesian coordinates by just choosing which symmetry operations you will perform and so on. So basically, at the end of the day, the message that I want to give you is that most of these models are very similar because all of them are based on the same founding principles that the potential energy surface should be smooth. So you need to use smooth cutoffs and widened Gaussians. You need to impose translational and rotational symmetries or invariances on your features. You need to make sure that you have completeness so that the feature space in which you're working spans the same Hilbert space as your positions. and so on. And finally, that they're all usually based on additivity and so on. So at the end of the day, different models will look very different, but the core features are exactly the same. They take your initial positions and they transform them into n-body correlation functions, and they perform some sort of regression on them. And with this, I would basically like to end the discussion on machine learning potentials. Do people have any questions? What is this tree called? It doesn't really have a name. There is a review by Michele Ceriotti. On machine learning potentials. I will share resources with you. I'll share a few reviews. Yes. Andrea, you have a question?
Yes.
What's a comment?
Actually, I have two, but like let's start with one. So does the method always try to optimize the total energy? Because like there are energy scales. So like if you are considering a cluster of water, for instance, or a box with waters, of course, if you change a little bit the position of oxygen and hydrogen in the same molecule, that changes a lot the energy, while the relative positions of water change the energy by very little. So, I mean, I think that on the total energy, you need to be very, very good in the intermolecular description before being able to optimize the intramolecular description before being able to fit the intermolecular ones. But the physics very often is mostly related with the intermolecular ones. So, I mean, is the one, do we need to go with brute force, or there is a trick maybe to optimize only the intermolecular sometime?
Yeah, so basically, no, I mean, actually, you generally regress on total energies. But the other thing that is very common is to regress on forces. You know, with the forces, you get the force acting on each atom, and that generally gives you much more information than the energies. Now, it has the same problem as you had mentioned, that the intramolecular energies have a very large length scale, or very small length scale, and very large fluctuations in the energies, while the intermolecular ones are much weaker. And I would say that people have tried both. And in my experience, learning the whole thing works just as well. You might want to ask why. And I don't know. I actually don't have a good answer to the why in that case, but it does seem to work really well. I would say that the devil again lies in the details always, and on your representations. You know, if your features or your symmetry functions are made in such a way that they can probe intermolecular interactions, you know, then they will not really contribute to very large changes in your energy, and they'll automatically, you know, only fit themselves to the long range or slowly varying interactions. So I guess if you have a good variety of symmetry functions or features, then it wouldn't really matter. Yeah.
Okay, so maybe I can do also the second question, which is on the symmetry functions. So the parameters on the symmetry functions, are they just taking like in a regular grid just to go to the point where you decide is the cutoff, or are they optimized somehow?
So they are not optimized while you are fitting the potential. These are called hyperparameters, and generally the way to do this is that you select a set of symmetry functions, you know, and for that you find what is the best model that you can get, you know, and the best model that you get is on the training set. Okay. After that, what you can do is you can manually modify these parameters, you know, and then you can find what is the best model that you get. And then for both the models, you can try to do a prediction on the validation set. So that's the set that none of these models have seen. And then you can choose the model which has the lowest validation error. So this is called a hyperparameter optimization. So basically so the parameters of your model, they are optimized on the basis of the training set, while these hyperparameters, which generally define the architecture of your model, or in this case, some of the features, dimensionality, etc., they are chosen in a way that they minimize the validation error. But I have to tell you that for most of these cases, the biggest thing is intuition, and with intuition, you can come up with a really good set of symmetry functions, and small changes to the width of the Gaussian or the cutoff doesn't make a very big change in the model at the end. A bigger error comes from the lack of data, as long as you have sufficiently spanned the space of configurations. I hope that answers that, Andrea.
So for instance, if you need to do liquid water, would be a good idea just to look at the peaks in the radial distribution function and set the positions to be matching those distances.
Yeah. I mean, all of these are used. Radial distribution function is actually, you can think of the radial distribution function as a symmetry function, to be very honest, because it basically is the sum of delta functions. But these are all Qs and very widely used to select the range, or where you would place your Gaussians. So yes, that's one of the most direct things that you would do. Is there any other question by anybody else? Yes, Kit.
What happens if the geometric change is very small? For instance, if you were looking at a polaron that localized a particular site and distorted, but the distortion was very small geometrically, is there a finite amount of cutoff that they would be able to detect?
Sorry, can you ask the last part of the question?
Would the amount of symmetry functions influence whether it was able to detect that or not?
Well, I mean, yes and no, because if we think purely in terms of a data-driven model, then the more symmetry functions you add, the higher is the dimensionality of your data, right? And then the higher the dimensionality of the data, the more are the possibilities of wiggling, right? If you have a very low dimensional model, there is no way you can overfit to anything, right? So in that case, a low dimensional model is very likely to give you very smooth representation of your potential energy surface, while a very high dimensional model is likely to give you more fluctuations in your potential energy surface. So yes, if you have a model in which you have a bit of overfitting, you are very likely to have big changes in your potential energy due to small changes. But if you have not overfit, and your choice of symmetry functions is sensible, then in that case, there shouldn't be a problem. What you might want to do practically is, if you know something about the polaron and the kind of distortions you have around a central atom, you may want to make sure that your symmetry functions can capture these distortions, that they can distinguish the distorted environment from a pristine environment.
Amazing. Thank you very much.
All right. Anyone else?
Yeah. So,
Yes, Nick?
When it comes to like getting the uncertainty out of it, I'm not exactly sure how getting an ensemble and then working out the mean and the variance of that, or the standard deviation, why does that exactly equate to an uncertainty?
Yeah.
Like conceptually, that doesn't.
That's a good question. Why does it relate to the uncertainty? There is a Bayesian way of proving it, actually, of why this will give you an uncertainty. And I have to say it's beyond the scope of this talk, but what I can do is send you a paper where it's described very well.
Yeah.
If that's okay. But one way of thinking about it is, have you worked with autocorrelation functions?
To a point, yeah.
So when you have an autocorrelation function, basically, if you compute your correlation time, that gives you that basically gives you an error in your time series, right? So the idea here is actually very similar. In this case, what you do is that you subsample randomly from your training set, and you try to fit various models, and you try to compute an uncertainty. And what you really say is that if all of my subsamples, subsets of my data set are completely independent of each other, then it doesn't, then I should get the true mean. But if they are correlated with each other, then this mean will be only proportional to the standard deviation. So, and you can show that by minimizing the Bayesian discrepancy, this relationship emerges out, where if you minimize, the likelihood function, which is a probe of error, right? You can show that the error actually is related to linearly with respect to your disagreement. So I'm happy to send it to you, but there is some correspondence between time series and this uncertainty error.
Yeah, I'd be interested to read that.
Right.
Thank you.
Yeah. All right. Okay. I think we have, we have exceeded the time, but if people have more questions, I'm happy to answer by email. I think you all have my email ID. If not, I will just type it here. So when I leave this Zoom meeting room, hopefully somebody else will become chair, and people who want to keep this will actually be able to see it. But yes, feel free to write to me if you have theoretical questions or more practical questions. Again, feel free to write to me. I will try to answer each and every one of these.